Hello, everyone. Today, I'll be talking about our work, interactive communication in bilateral trade. It's a joint work with Jieming and Renato Paes Leme from Google. We mainly consider the bilateral trade game, where we have Sally, the seller, and Bob, the buyer. Sally has a private cost for an item, theta S, drawn from the distribution ds. And Bob is interested in buying the item, and he has a private value, theta B, drawn from a distribution dB. The distributions ds and dB are public information and are known to both players. And in the end, Sally will choose her action by choosing a price P. And then Bob, upon seeing the price, will accept if his private value theta B is greater than or equal to the price P. And if there's no trade, then both players will get zero utility. And if there is a trade, then Sally will get utility of P minus her cost theta S, and Bob will get utility of theta B minus P. So we can depict the situation in the following figure. In the case where theta S is less than theta B, we can write down the price on this number axis. So if the price is less than the cost, or if the price is higher than the value, then there won't be a trade because one of the players won't be willing to take the trade. And if P lies between theta S and theta B, then there can be a trade. And in that case, Bob wants the price to be lower and Sally wants the price to be higher. And we know that the sum of utilities is a fixed number, which is value minus cost. And in that case, the trade is efficient, but the players want to push the prices into different directions. So in this bilateral trade setting, from the revelation principle, we can say that interaction is not useful, and we might as well just use a direct mechanism. And from the Meyer-Synthetic theorem, we know that we can't design mechanisms that always allocate whenever the trade is possible. So we can't always get the efficient solution in this game. However, in reality, there are a lot of bargaining processes going on. For example, the car dealers and real estate agents have jobs based on bargaining. And our goal of this work is to design a model of bilateral trade that captures the power of this interactive communication. So for this purpose, we will introduce a new ingredient, which is the Bayesian persuasion model. In this model, there is a receiver and a sender. The sender knows some state of the world data drawn from a distribution D. And in the end, the receiver will take some action A from some action set A. And then the receiver will get a utility of US data A, depending on the state and her action. And also the sender will get utility UB, depending on the state and the action as well. So in the Bayesian persuasion model, the sender can choose to send some verifiable signal sigma correlated with the state to update the receiver's perception of the state of the world. And then upon receiving the signal, the receiver can choose her action to maximize her expected utility conditioned on receiving the signal sigma. And there's a famous special case of the Bayesian persuasion setting introduced by Bergemann-Brooks-Morris. And this setup is for selling an item. So Sally is trying to sell one item to Bob. And Sally always has a fixed cost for the item, but Bob has a variable value for the item, drawn from a distribution dB. And in the end, Sally will choose a price P for the item, and then Bob will accept if his private value is greater than or equal to P. And if there's a trade, then Sally gets utility of P minus her cost, and Bob gets utility of his value minus P. And Sally will choose her price P to maximize her expected profit, which is P minus theta S times the probability of the trade. And in this model, we let Bob send some signal beforehand, depending on his private value on item. And then Sally will get the signal, and then she will choose the price P to maximize this conditional expectation. So she will maximize the price minus her cost times the probability of Bob buying the item given the signal. And the main result of the paper of Bergemann-Brooks-Morris can be summarized in the following sentence. So Bob has a way to send the signal so that the trade will be efficient, and Bob will be the one to capture the remaining surplus from trade. And we generalize their model in the following way. So now Sally no longer has a fixed cost, but has her cost drawn from some distribution ds as well. And in that case, we can view the model in the following perspective. So in the beginning, Sally has some perception dB on Bob's private value, and Bob has some perception ds on Sally's private cost. And then Bob can send some signal sigma to update Sally's perception. And Sally, when she receives the signal, she will update her perception about Bob's private value into this dB prime. And then she will set the price P depending on dB prime and her private cost. And we can further generalize this model into the so-called Bayesian conversation, in which there are multiple rounds of sending signals. So you can say in the first round, Sally sends some signal sigma prime, depending on her cost, to Bob. And then Bob will update her perception of Sally's private cost into this distribution ds prime. And then in the second round, Bob can send some signal back to Sally about his private value. So Sally will then update her perception into dB prime. And then finally, Sally can set the price depending on dB prime and her private cost. And we can further generalize the conversation into having many rounds. And in the end, Sally will set some price P. So now we formally introduce our model of interactive communication. So in the base game, there are two agents, Sally and Bob. They have type spaces, theta S and theta B, and their types are drawn from independent distributions, ds and dB. Sally has an action from the set AS, and then the final payoffs are the functions US and UB, depending on the types theta S and theta B, and also Sally's final action AS. So the communication is an alternating protocol where Bob sends messages in odd rounds and Sally sends messages in even rounds. So for example, in the second to last round, Sally sends something to Bob, and then in the final round, Bob sends something back to Sally. So a message from Bob to Sally is a refinement of Sally's information about Bob. So in the message from Bob, it can depend on Bob's information about Sally and also Sally's information about Bob. And then it will output a distribution of Sally's information in the next round as a refinement of Sally's information. And we require Bayes plausibility in the model. So we require the posterior to be equal to the prior. And similarly, we can define a message from Sally to Bob, and that should be a refinement of Bob's information about Sally. And still, we require Bayes plausibility. And we can define the payoffs with communication in the following way. So let pi it dsdb be the utility for player I in a T-round protocol when the perceived distributions are ds and db. So for an odd T, it's the turn for Bob to send the message. So that should be the expected pi I to the t minus 1 ds db prime, where db prime is updated by Bob's message in the round. And for even t, we can define it similarly. That's the term for Sally to send her message, and she will update Bob's perceived distribution to ds prime, and we take the expectation over pi I to the t minus 1 ds prime d. And for the equilibrium concept, we adopt a concept similar to the subgame perfect Nash equilibrium, where the agents choose messages to maximize their payoffs. And in our work, we assume the receiver can always choose to refuse to hear any message. And also ties are broken favorably to the other plane. And now we can define a concept called message complexity. So we notice that in equilibrium, agents will always weakly improve their payoffs with more rounds. So for any agent I, pi I to the t plus 1 is always greater than or equal to pi I to the t. And that is because for the message sender in each round, he or she can just choose to send nothing to the other player to guarantee the same payoff as in the setting where there's one fewer round. And for the receiver, because of our assumption that the receiver can always choose to refuse to get the signal, we know that the utility is always monotone as well for the receiver. And that allows us to take the limit of the payoffs because the sequence pi I to the t is monotonically increasing. So we can define the limit pi I to the infinity as the limit payoffs. And finally, we can define the message complexity in the following way. So it's just the smallest number t, so that pi I t equals the limit payoffs for each agent. And in totally, that just means having more rounds than t will not help anyone in the setting. And our main result can be summarized in the following sentence. Agents won't stop communicating until they reach an efficient allocation. And mathematically, we are saying that if we have a finite message complexity, then the final allocation will be efficient. So the limit payoff for Sally plus the limit payoff for Bob will be equal to the maximum efficiency we can gain from this trade. And our main result leaves the following question open, and we summarize it as a conjecture. So we conjecture that the message complexity is actually always finite for any distributions with finite support in this bilateral trade setting. And if this is true, then we know that interactive communication always ends in finite rounds, and it's always leading to efficiency. And also, if this is false, then we know there are settings where agents would prefer to have an infinitely long conversation before making a trade. And in our paper, we also have the following result. If Bob's type space has supersize of 2, then we can fully characterize the communication structure of that game. And in that case, the message complexity is always at most 2. And now we briefly introduce our proof techniques. So for our result that finite message complexity leads to efficiency, we can use the following recursive argument. So for the base case where message complexity is 0, we can easily show that the allocation must be efficient. And then we use the recursive argument that if there's a protocol of a finite message complexity t, then we can construct another protocol of message complexity t minus 1, also leading to an inefficient outcome. And therefore, by this recursive argument, we can show there can't be any protocol of finite message complexity leading to inefficient outcome. And for our other result of fully characterizing the case where Bob has a supersize of 2, we characterize the dynamics of alternative concavification, and that can be viewed as a higher order version of the indifference argument in the work of Bergemann-Brooks and Morris. And in the end, we want to introduce another game called the spy game as an example of complicated and long communication. So in this game, we have Sally, the spy master, and Bob, the bird watcher, and their types are drawn from 0 and 1. And we can view that as two separate countries, country 0 and country 1. And in the end, Sally's actions are to cooperate with Bob or to expose Bob. And the payoff matrix is like this. If they are from the same country, then Sally wants to cooperate. And if they are from different countries, then it's like a zero-sum game. And Sally wants to expose Bob. And initially, we assume DS and DB are both half, so they have equal probability to from both countries independently. And we implement some experiments in this game, and it shows that in equilibrium, the communication protocol is quite long and involves gradual disclosure of information. And we conclude our talk by repeating our main message, which is long interactive communication can improve outcomes and can often lead to efficiency. Thanks for listening.